Hello, welcome back. In this segment, I want to talk about zero knowledge proof. I wanted to take an example, for instance, discrete logarithm problem that we talked about. And it's a hard computer science problem. As far as we know, there is no known polynomial time algorithm that can solve this problem that suppose somebody gives you a value y, which is equal to g power x, and they ask you to find x given y and g. G is a group generator that we talked about earlier. Okay, it could be any cyclic group. Okay, so the discrete logarithm problem is given y, find x. Okay, this is a challenging problem. If we solve this, we are breaking cryptography. Okay, all right. So this problem, since it's considered to be a hard problem, can also be used now for building other cryptographic constructions. For example, for authentication. Suppose you would like to know whether I know the value of x. Okay. Of course, I don't want to share my x with you because x is a private value, and but still you wanted to be convinced that I know the value of x. Okay, so that's basically the motivation. Okay, how can I prove that I know the value of x without showing you the x itself and leaking very limited information about the x? Okay, so you may not know much about x, but you can still confirm through probabilistic reasoning that very likely I have the value x with me. Okay, that's the idea of zero knowledge. I'm not going to talk zero knowledge from a pure computer science perspective because it's very, very rigorously defined, but I'm going to keep it a little bit informal. So at a high level, the goal is to show to one party that you know the value of x, but without giving the value of x to the other party. Okay, so I'm also going to deviate a little bit from Alice and Bob discussion in the context of zero knowledge proof. The literature usually uses these two characters, Becky and Victor. Okay, the reason for their choices will be clear. Why we call them Becky and Victor. Okay, you can imagine Becky is the one who's trying to prove that she knows the value of x. Okay, this is the proving problem, right? You want to prove to others that you know the value of x, but without disclosing x. Okay, so Victor is the guy who wants to verify whether Becky actually knows the value of x. So that's the reason we use Victor, V for Victor. Let's proceed further now to design a zero knowledge proof that Becky indeed knows the value of x and Victor can verify, and Victor cannot use that knowledge to convince others that Victor knows the value of x. That's the idea. Okay. All right. So how do we proceed? Let me formalize this a little bit more. I need to specify more notations carefully. Becky and Victor have to agree on some common things like the common group generator. We have the group G, the cyclic group, and the order of the group is Q. Okay, there are Q elements in the group, and we will need a generator for the group. Okay, let's G be the generator. Okay, so G is the group, Q is the order of the group, and G is the generator of the group. Okay, this is something both Becky and Victor have to agree, and Becky must also publish the value of y. Okay, y must be published to everybody. Assume there is a trusted public file where Becky can say, here is Becky and this is the value y. Okay, you can imagine y as some kind of a public value. Okay, this is public, nothing secret about it. Okay, the value that is on the top, the x value, is the private values that she wants to convince that she knows it. How do we proceed now, given the fact that we don't want to share the value of x to Victor? So I have actually developed a sequence diagram to explain this more formally, but let me first draw this informally. Okay, so the first step in this process is actually Becky picking a random number r from ZQ, meaning from 0 through Q minus 1, including Q minus 1. Sometimes choosing the value r being 0 is not good, but in general, that will not happen. Almost impossible chance that r is 0. If you randomly choose an element from a large group, there's a negligible probability r is 0. So I will stick with being a little informal. R belongs to ZQ. Okay, ZQ means all values from 0 through Q minus 1. What will she do? She will compute something called C, which is G power R, okay, in her group. Okay, let's say the group is based on a multiplication of numbers, so the finite field of multiplication. Okay, so in that case, multiplying two numbers means they multiply the numbers and then take the remainder with mod p. Okay, so the way we construct the group of order q is as follows. We take p, this is p equal to 2 times q plus 1. Okay, q is the cyclic subgroup of order q. Okay, this is the order of the cyclic group spawned by this generator G. And we publish P also to the world. Everybody in the world knows P and Q. Okay, that's the idea. Anyway, so G power R mod P will be the value Becky will compute, and then she will send that value to Victor. Okay, so Victor gets the value C. Okay, what will Victor do with the value C? Victor can make a decision here. Victor will actually create a random value V, which can be in something like a 0 or 1. Okay, either 0 or 1. Okay, so if Victor gets a value, let's say Victor's value is randomly chosen from Z2, meaning either 0 or 1, only one bit value V, small v. Let's say if Victor is getting a value to be 0, he will send that to Becky. Okay, so Becky will get either 0 or 1 from Victor. Now Becky has to make a choice. If Victor sends 0, let's say Becky is going to send back x plus r, x plus r. This is important. X plus r in mod q. Okay, the order of the cyclic group is q. Remember, that's the reason why we picked the cyclic group of order q. So she's going to send back this. If Victor is sending 0, which means Becky has to send x plus r. But on the other hand, Victor is sending 1. That means Becky has to send just the value r. Okay, so if Victor sends 0, Becky has to reply with x plus r. If Victor sends 1, Becky has to reply with the value r. Okay, Becky doesn't know which one Victor is going to ask for. Victor may ask for x plus r or r. Okay, that's an interesting point. I will come back to that. Okay, so now what will Victor do with it? Suppose let's assume Victor sent the value 0, which means he expects x plus r to be back from Becky. Okay, what will Victor do with it? Victor will now check whether Becky really knows x. Okay, but Victor can't take x plus r and extract x because he doesn't know r. Okay, because he asked only for x plus r. So that's the important point to keep in mind. So what will Victor do with it? Say, let's assume Becky sent x plus r when Victor was asking for it, right? So what all Victor has to do is he knows the C that he got from Becky, right? So he takes the C and he multiplies it with y. Y is also public. Remember, y is public. Y is g power x. So he multiplies these two, and what is the multiplication of these two will be? C is nothing but g power r. Y is nothing but g power x, right? So if indeed Becky knows x, then this value must be equal to g power x plus r. Okay, mod q mod p. Okay, let me explain why I put a mod q on top and mod p at the bottom. So remember, whenever we compute exponent, for example, suppose you have a group which is a cyclic group of order q, and if you want to compute g power x or whatever value g power say a general g power a mod p, it's same as computing g power a mod q. Okay, if the order of the group spawned by G is Q, then it's enough to just compute G power A mod Q mod P. Okay, the mod P is always here. Okay, so this means Victor can be confident that okay, possibly Becky knows the value of, I said possibly for a reason. In a moment it will be clear. And if Victor was just asking for R, meaning he sent 1, then he can check whether the R is correct, right? All he has to do is check whether is C is equal to G power R. Okay, because C is already published in the very first step. And if Becky indeed knows R, the C should be equal to G power R. Okay. All right. Victor will repeat this process. So this whole thing will run in a loop. Okay. several times. As many times Victor wants to get confidence that actually Becky knows the value of X. So he can gain more and more confidence by running this multiple times. In my demo, I'm just running it for 50 times because it's impossible for Becky to cheat this step every time, unless she has a magic to predict what is the value of Victor will ask is 0 or 1. If Becky knows what value Victor is going to ask, then she can easily cheat. I'll show you how in a moment. But for now, let's consider the correct case. If Becky knows the value of X, she can convince Victor that she knows the value of X. But in this process, she never exchanged the value of X. As you can see here, X is never exchanged. This line shows X plus R, right? From X plus R, you can't extract R. You can't extract X. You can't extract R. Okay, both are private. Remember, X is private, R is private. Unless the value V asked by Victor is 1. Okay, Victor may ask for 0. That means Becky is going to only send X plus R. But here's the catch. Suppose there's a mistake in the random number generation process, then you're in deep trouble. Let's say Becky made a programming mistake. Instead of putting the R inside the loop, she put it outside, which happened in many systems. Now it's easy to break because somebody who's monitoring this traffic, okay, would know, okay, here is X plus R, and they already, let's assume, already captured the R because there was a previous request from Vector with the value V being 1. That means Becky would have sent R in clear, right? This is all clear text anyways. So all the attacker has to do is just take X plus R and subtract by R, because R is public. In the previous run, R was passed because maybe Victor was asking for a value R by sending a bit 1. All the attacker has to do is just subtract these two and get the X. Okay, this is bad, and then you can cheat. Okay, that's the reason why R should not be out of the loop. Okay, that's one attack. And then now another attack is that, remember, the first message is coming from Becky to Victor. If you change the order in messages are exchanged, for example, if Victor was the one who sent a 0 or 1 first, the whole thing is broken right away. Let me give you one example. Let's say, for example, somehow Becky knows what is the next bit Victor is going to ask. Okay, 0 or 1 are the only two possibilities. Let's assume Becky is able to predict the next bit is going to be a 0 bit, okay, from Victor. So what she can do is, without knowing X, she can prepare a message like this. Okay, the message she can prepare is as follows. She generates a random number R prime, okay, and computes G power R prime, okay. It's nothing to do with prime number. R prime means just another random number, and multiply it with Y inverse. These are all publicly available data. Y is public, therefore Y inverse is also public. You can compute Y inverse in mod P easily. So she's going to return this as the C value, okay? This is the new C value. She's going to pretend like this. So if Becky was able to predict the next value from Victor is going to be 0, instead of sending G power R mod P, she's going to send G R prime times Y inverse to Victor. Okay, now Victor is getting this corrupted C, which doesn't have any X here, right? But still, what he's going to do, he's going to multiply that C by Y. So when it multiplies with Y, what happens? This Y inverse and Y will cancel out. What is left is just G power R prime, right? G power R prime is, what is left is just, when you multiply it with Y, this Y and the Y inverse will cancel out. So you are left with G R prime, okay? So this side will be just G R prime, okay? And now look at what happens. Instead of sending X plus R, of course, she will just send R prime, okay? Which is exactly what Victor is going to replace by, because Victor thinks, okay, I asked for X plus R by sending a bit 0, but Becky was able to predict what is going to come, so she already put a backdoor inside the C. Therefore, what Victor will not be aware of this mistake, and over the superscript where he is supposed to do G power of X plus R mod Q, he's going to do G power R prime. That means here is the left hand side is G power R prime, right hand side is also G power R prime, both are same. So Victor thinks Becky knows the value of X, which is wrong. Becky indeed doesn't know the value of X, but she can cheat. That's the reason why the random number generated by Victor should be unpredictable, okay? Which is also another reason to explain now that why this has to run many times, okay? Suppose Becky was able to make a guess of the next bit, right? Okay, Becky has magic and found some weakness in the Victor's random number generator, so she was able to predict the next bit. In that case, she is going to win. But winning once doesn't mean much in this setup, because we are going to run this again and again, unless Becky is really good in predicting all the sequence of zeros and ones that come out from Victor, which is impossible if you use a truly random number generator, at least close to pseudo random number generator. Then there is a high confidence that Becky can demonstrate to Victor that she knows the value of X. Okay, or anyone who knows the value of X can convince Victor without sharing the value. But in this process, what is the knowledge Victor acquired? Not much. I mean, Victor has some mathematical equations, you know. He knows how X plus R for a random R, for a one particular R, mod Q is, but that is not so much knowledge that he can use to beat Becky and pretend like a Becky in other contexts. That's basically the idea of zero knowledge proof here. It's a kind of a probabilistic framework. Victor is making a choice here, right? He can either send a 0 or 1. So between 0 or 1. Becky doesn't know which is going to come, therefore she can't put a backdoor inside the C that she's sending. If Victor sends 0, he expects the reply to be X plus R, otherwise he expects the reply to be R, which he can check it easily because he's the one who sent the V first. And once he gets the X plus R for the case that he asked for, he can just do C times G, Y and check whether that is equal to G power X plus R mod Q. This is only equal if C has the value of, if only she knows the value of X, this can be done, right? Otherwise, she can't, because she is the one who is going to send X plus R mod Q, which is not possible if you don't know X, okay? All right, that's all. So let me show you the formal sequence diagram, and then I will run a quick demo of this setup. I prepared a Python program for it, okay? All right, so here is the nice sequence diagram. I hope you like this sequence diagram. Here are our participants, Becky and Victor. The goal of Becky is to convince Victor that she knows the value of the X, which is the exponent used in Diffie-Hellman key exchange, for example. In general, the discrete log problem, right? So remember the problem again. Given Y, your goal is to find X, okay, in the context of a cyclic group generated by the element G, okay? So as I mentioned on the whiteboard, the loop is running here. Becky generates a random number R. She sends G power R in mod P to Victor. I'm not writing mod P again and again to Victor. Victor tosses a coin. You can imagine like this. If the value is 0, he expects Becky to return X plus R in mod Q. Otherwise, let me go down a little bit here. Otherwise, he expects Becky to return the value R. Okay, that's the reason why you have the alternatives. So in case he asked for X plus R, he can go and check it by doing the simple operation C times Y equal to X power X plus R in mod Q. If it is not equal, then you know for sure Becky is cheating, because this mathematical equation is not valid. And the other case is that if somebody else is pretending like a Becky and injects some traffic, we can also check that, because their C will not be equal to G power R, because they wouldn't know the value of R. Okay, and remember, R is generated every time unique in the random in this process. Okay, and it's also interesting to connect to birthday paradox. If you use a weaker random number generator or random number generator where the strength is small, then the value of R will repeat, which means X plus R will give you the X, okay, if you know the R, of course. That's the reason why you need to have a very strong randomness and not change the order in which you exchange the random numbers, okay? Otherwise, the C can be backdoored by Becky without knowing X, okay? Now let's do a quick demo of this, and I think that will be fun. So I put together this little code, right, to explain to you how I programmed it. I created 2 threads, one for Victor, another for Becky. So I used the message queue logic. Okay, so Victor is first, let's start the process. Becky first generates a random number R, computes G power R mod P, puts it to Victor. And then she's waiting whether whether there is any signal termination. This is basically a way of checking whether other side is done. This is very Python specific. You don't need to know, and it's not related to zero knowledge proof at this point. If Victor sent a message, okay, give me x plus r, Becky is going to compute x plus r. Otherwise, she's going to just compute the value of r and put it into the outgoing queue. Okay, so it means Victor will read the incoming queue and extract the value C sent by Becky. He generates a random bit, either 0 or 1, and then he puts it into the queue that will be read by Becky. And now he checks if he asked for x plus r, right, by sending 0 bit, meaning he's asking for x plus r. He checks whether the incoming message is indeed x plus r, okay, by doing this multiplication of C times y, and checks against G power S. That's what we talked about on the whiteboard. S is the number, either it could be x plus r mod p or r. Okay, let me explain what S is one more time clearly. S is the choice that that Becky will make depending on what Victor has asked for. Okay, if Victor says give me x plus r, Victor is going to do that. If Becky is going to do that. Okay, that's basically it. Now let's run it for only one round. Okay, just for getting the print messages across. Okay, as you can see, Becky sends to Victor the value C. Victor got the value C, and he's going to use random number generator. It turned out to be saying 0. That means Becky is sending back x plus r, right? Otherwise, she will be sending r. Okay, now the next step is Becky sends Becky sends to Victor C. Victor is checking whether did Becky send me R, and then he's going to stop the process. Okay, because we are running it only once. Okay, so that's basically it. Okay, so it's fun to inject some false and look at the behavior. Let's run this once. What happens if you run it once and try to cheat? If you are Becky and don't know the value of x, okay, let's do like this. We just send r in both cases. R is just some random number. Okay. Oh, in this attempt, the very first case, it's failed. Let's try again. Okay, it failed again. Let me check. There is some mistake somewhere in the code. Okay. I have an assertion. That's the reason why it's failing. Okay, that's good. So kept failing here. Let me try. Yeah, now it comes. Maybe the first 3 random number bits were 0, 0, 0, which is not quite unusual. See here, the verification process succeeded, even though in our case, we are pretending as if Becky doesn't know the value of x. Okay, we were sending a random r instead of x plus r, and still the verification succeeded. But this wouldn't happen if you just increase the number of rounds, say increase it by 50 times. That means all of the 50 times she has to get it right, which is close to probability of 0. If you think about it, the probability will go down because you can't keep on predicting the next bit correctly. Okay, as you can see, it's failing right away. So this is good. Okay, all right, that's basically it. Now let's get back to the correct version and run it 50 times very quickly. Yep, all of the 50 times Victor was able to check whether Becky knows the value of x. Okay, maybe in that 50 times, not every time is a valid check, right? So because she could have guessed the next bit and then send it that random r prime that I talked about, but it's not possible for her to check to get the correct value of the next bit Victor is asking for. That would be impossible to do if it's a properly generated random number sequence. Okay, that's the idea of zero knowledge proof.